All right, so now we're going to talk about the Riemannian-Newton method for real-valued functions. All right, so in particular, that means that we're looking at a case where the vector field, which you're trying to find the zeros of, is given by the gradient of the function f, right? So C is equal to grad f, okay, where f is a real-valued cost function. On the Riemannian manifold M. Then when that happens, the Newton equation, which defines the Newton search direction, has the form. So the Newton equation is given by the following. So the Hessian of f of xk times eta k is equal to minus the gradient of f at xk. Okay, so where the Hessian f of x is viewed as a linear map from the tangent space at x to the manifold back to itself, right, which maps a vector to the covariant derivative of the gradient of f. Okay, so this is the Hessian, sort of Riemannian Hessian of f at x for the affine connection. Nabla. Okay, so I'll write this down as an algorithm, but you can think of it again as a particular case of the previous algorithm we had discussed for the geometric Newton method for vector fields. Okay. So this is the Riemannian-Newton method. For real-valued functions. Okay, and you provide the algorithm of the following. You have a Riemannian manifold. M, okay, you have a retraction R on M. You could supply it with the exponential, the exponential, if that turns out to be easy to compute. Otherwise, you can just have sort of, you can substitute that with a retraction. You have an affine connection, nabla, right, on M, and you have a real valued function. F on M. Okay, and then the goal is to find a critical point. Of F, right? So that's basically some point x on M such that gradient of f at that point x is equal to 0. Okay, and then the input is again your iterate, initial iterate, x0 in M, and then the output is a sequence of iterates. xk. Okay, so again, for k equals to 0 and so on, you do the following. You solve the Newton equation. Right, which is Hessian, right, this Hessian of f of xk and eta k is equal to the negative the gradient of f at xk. Right, we solve this for eta k, which is in tangent space of at the point xk to the manifold M, and then the Hessian is defined as follows. So it's defined to be the covariant derivative of the gradient, right, of fk, which is what I had here. Right, and then use, okay, so once you have that Newton direction, you set the new iterate xk plus 1 as the retraction at the point xk of this Newton direction. Okay, and then you end the for loop. Okay, so, right. So the point is that, or the issue, if you will, is that this Newton vector, right, isn't necessarily a descent direction. Okay, so, all right, so let's see a little bit about that. So in general, right, this, the Newton vector is not necessarily a descent direction. Of the cost function. Okay. All right, so let's just see what happens, right? So if you take this derivative in this search direction, this is equal to the gradient of f at xk in this direction, right? And then we have an expression for what that is, right? So this is equal to minus grad f at xk paired with the inverse Hessian, right, applied to the residual, well, applied to grad of fk, right? Right, that's just the definition. Going from here to here just uses the Newton equation here, right? No, sorry, this Newton equation here. Okay. And this is not guaranteed. To be negative, which is what is necessary for it to be a descent direction. So we need additional assumptions on the Hessian. On the Hessian operator. Okay, so a sufficient condition for this to be a descent direction is that the Hessian is positive definite. And what that means is that this expression, right, is always greater than 0 for all vectors which are not 0. All right. So so let's say what we can say if we pick particular choices of the affine connection. So of course it's like the Hessian depends on the affine connection. So whether or not this Hessian is positive definite depends, at least in part, on your choice of affine connection. Okay, so without knowing what that affine connection is, right, we can't make a definitive statement about whether or not the Hessian is going to be a positive definite operator. Okay, so but let's look at a specific case, right? So when nabla is a symmetric connection, symmetric affine connection, and I should remark that the Riemannian connection or the Levi-Civita connection is an example of a symmetric affine connection. Okay, so if you use the Riemannian or Levi-Civita connection or any other symmetric affine connection, then the property that the Hessian is positive definite right, is positive definite if and only if the following is true. If and only if all its eigenvalues are strictly positive. Okay. All right. All right. So so what oftentimes happens is that you know, for practical purposes, what one does instead to get practical convergence results, okay, is to essentially modify the Newton equation. Okay, and let me sort of say how you do this. So in order to obtain practical convergence results, right, so quasi-Newton methods have been proposed where the update vector is given by the solution of the following equation. So you modify the equation slightly. So instead of just having that the Hessian of f at xk paired with the update vector is equal to negative of the gradient of f, right, I sort of shifted a little bit by another operator. Okay, where ek is chosen to make this combined operator positive definite. Okay. Okay. And the point is that for suitable choices of ek, then what will happen is that the search directions you obtain from this will then be gradient related. And then that, as you recall, it's like in the proof of convergence, it's like for the line search algorithm is important for global convergence. Okay. All right. So let me sort of make some remarks about this. Okay, so the remark is that with suitable choices EK, right? The sequence of search directions, right, is gradient related. And you recall that property was important in proving the global convergence of line search algorithms. So this is an important condition in the proof of global convergence. Of line search algorithms. Okay. So, but the point is that you have to be careful. It's like in what you choose for the EK, so that you don't mess up the other nice property of Newton methods, which is that they converge really fast, right? So you need care must be taken in choosing EK, right? So that it maintains the superlinear convergence. Properties of the Newton method, of the pure Newton method. Okay. All right. So so that's basically what I wanted to say. It's like in terms of just framing the basic sort of Riemannian Newton method for real-valued functions. And then the next thing which we'll talk about is the local convergence of these methods. So let me just stop here for now.